My name is Matthias. I'm a professor in soft condensed matter physics at the School of Physics. So I deal with squishy materials. These materials are, for example, foams, emulsions, granular media, suspensions, and so on. There's a wide range of these materials. What they all have in common that they're not quite perfect solids nor liquids. They're kind of in between. And there's a lot of interesting physics hidden beneath. And I'll talk about one particular material, which is granular media. So you all know sand, I guess. That's one example of it. And I'll talk about two phenomena that can occur in this material. So let's just go through what granular media actually are. I mean, these are collections of macroscopic grains. Yeah? So they can range from micron size to millimeter size, and there's solid friction between them, and the collisions are inelastic. Yeah? So when they collide, they lose energy, much like when you drop a ball on the floor, it doesn't come back to the same height. Yeah? And so without externally forcing this sand or this granular medium, it comes to rest and doesn't move. Yeah? So it's not in thermal equilibrium. So there are a lot of substances in physics we deal with that are in thermal equilibrium that makes things easier, as you may learn later on. But here we don't have that, which makes it actually a difficult subject to study. Now, you all know beach, beaches, so luckily we don't sink into the beach when we walk on it. Yeah? It's powdery, but it still acts like a solid. We don't sink in. However, if you look at an hourglass, for example, here it's solid-like, but it can flow through this orifice. So here it's a liquid-like behavior, even gaseous behavior, and then it turns into a solid again. Also here you see some ball bearings that are tilted, and you see a flowing region here and a solid-like region here that coexist. Yeah? And this is very different from ordinary liquids. Yeah? If you think of water, for example, water is liquid at room temperature and turns into solid ice below 0 degrees. But here you can have both of these behaviors at room temperature, and they can coexist. Yeah? So this behavior is quite different from ordinary liquids. Yeah? Now, why should we care? I mean, there are various reasons. There are some practical reasons, for example. If you think of industry, yeah, powders are used in 80% of manufactured products at some point during their processing cycle. Yeah? I mean, for example, aspirin pills. These are different powders mixed together, pressed into pills. Yeah? The active ingredient is actually just a little part of this tablet, and the rest is basically a carrier substance to make it, you know, some size. Yeah? Then also, if you think about processing powders, yeah, bringing them from place A to place B, you want to understand how these powders flow, yeah? And we don't really understand this properly. For liquids, we have what's called the Navier-Stokes equation that you can solve, at least numerically. But for sand and other types of granular media, we don't have such a thing. Yeah? And then for physicists, there's also an interesting system because if you think of ball bearings that are packed in a disordered state, yeah? The structure of these ball bearings, and that was actually studied by Irish physicist Bernal in the 60s, this structure of these ball bearings, this disordered structure, is essentially the same structure you find in a liquid. Yeah? For example, water, when it turns into ice, it forms an ordered crystal structure with long-range order. If it's a gas, you know, they're far apart, these molecules, but in a liquid, they're fairly close together, but they're disordered, and okay, they move around, but the structure is very similar what you would find if you just look at sort of a macroscopic system of ball bearings. Yeah? And Bernal actually used this to understand ordinary liquids better. He he put this into some box here, the ball bearings, poured some liquid paint in, and then looked at the contacts, for example. Yeah? But so there's quite a history in physics studying these type of systems, and also the engineers, of course, are quite keen on better understanding these type of systems. Now, I just want to give you some simple example to illustrate how different they are. For example, one of the oldest laws in physics is Torricelli's law, 1643. Yeah? It just says that if you have some container with a liquid and you poke a hole at the bottom, the liquid obviously flows out because there's hydrostatic pressure acting here at the outlet. And the flow velocity is simply the square root of 2 times gravitational acceleration and the height of this liquid column. Yeah? So note, I mean, you don't have to understand here the details, but it depends on the height of the liquid column, because the higher the column is, the more pressure is acting on that outlet. Yeah? Now, if you do the same for granular media, and that took more than 300 years, actually, to somebody to do that, yeah? So you get what's called Bevelou's law. That's a Belgian engineer. So if you do this with sand, for example, you get quite a different law. Yeah? It still depends on gravitation, as it should, but you will see that the height of this granular column does not appear. Yeah? So you can pile this a kilometer high, and the flow rate will not change. Yeah? And that is very counterintuitive, because obviously the sand does have some weight. Yeah? And you would expect that the higher you pile this up, the larger the pressure here is at the outlet, and the faster the sand should flow out, but that's not the case. So the flow rate is independent of the height. Now this is a very curious phenomenon, so why is that? Yeah? And obviously this would be important for processing, yeah, these materials. So you can put a pressure sensor here at the bottom and see what happens to the hydrostatic pressure. So pressure is just the force per unit area. Yeah? And as you can see, for water, it just linearly increases with the height, as you would expect. Yeah? That's the ordinary hydrostatic pressure. Yeah? So it's also, if you go diving, right, as you go deeper and deeper, you feel the pressure increasing on your ears. It's typically like 1 atmosphere per 10-meter depth. If you do the same now for sand or for other grains, what you will see, it initially rises, but then the pressure saturates and plateaus and becomes constant. Yeah? Now, but why is that? I mean, obviously the weight of this whole granular column is increasing with height, right? So the weight has to go somewhere, yeah? And, but it's not going to that pressure sensor, apparently. Yeah? So what's actually happening is that the weight is supported by the walls. Yeah? Remember that these grains have solid friction between them, and there's also solid friction with the side walls. Yeah? And here, for example, I've shown a picture where this is illustrated. So this was done by Bob Berenger's group in the US. So they used what's called photoelastic discs, and I don't want to go into detail, but you put it through cross polarizers, and when these discs deform, they twist the light a little bit, and so the regions of high force appear yellow here in this picture. Yeah? So these are a bunch of grains. You can probably you can't see them, but this is basically a way to visualize the forces inside such a packing. Yeah? And you can see that you have these high forces, and they terminate all at the wall. Yeah? And then you have also regions where there's actually almost no force. So it's a very heterogeneous system. And so essentially what happens is here that the weight of this granular column is mostly supported by the side walls. Yeah? So you have a kind of arcing effect. And that is essentially due to solid friction. And well, that's important if you want to build a silo, for example, because if you don't build it right, it just collapses. Yeah? So building a silo for grains is very different from water, yeah? Because the walls here have to be much stronger. Yeah? Also, hourglasses, for example, you may wonder why people don't use water or something for an hourglass. but as you can see here, the flow rate now we know is constant. Yeah, so you can make the spacing at equal distance, the minutes here, because the flow rate doesn't change with the height of the granular column. For water, that would be different, yeah, because as the column decreases in height, the flow rate would slow down. Now, here, for example, now I want to talk about jets. So we all know water jets from the tap, for example, and they usually become unstable and they form droplets. The reason for that is surface tension. So surface tension essentially is a thermodynamic phenomenon, and it's because that water molecules like to be surrounded by their bodies, yeah? And the ones that are at the interface, they have less neighbors and they don't like that. So basically, a liquid always tries to minimize its interfacial area, surface area, yeah? And that is the reason why you get this so-called Rayleigh plateau instability, because if you put a wavy surface onto this liquid column, it turns out that for a certain wavelength, the area is actually minimized, and so the system goes towards that wavelength, and then it eventually, this will snap off into droplets, and the size of these droplets are of the order of the jet diameter. Yeah? But here the point is that you need surface tension for this to occur. Now, if you do this with sand, sand is not a thermal system, so it doesn't really have surface tension. So you would not expect to see this same phenomenon. What you see here is a 1-inch steel ball dropped into a granular medium. You see this jet coming up, and then look how this breaks up into droplets. Yeah? And this is a very generic phenomenon. You can do this also here just with a funnel. Yeah, so here you just have some grains going through a funnel, and you see a camera that is in free fall moving with a jet, a high-speed camera, $80,000 dropping 20 meters, not 2 meters. Yeah, somebody catching it. So you can see how this, it stretches due to gravity, and then eventually it snaps off into these droplets. Yeah? They're maybe not quite as round and nice as the water droplets, but nevertheless they're droplets. But it's not clear why this should happen, because there's no surface tension. Now, it doesn't always happen. Yeah? So if you do this, for example, with copper beads, yeah, then this is maybe more what you would expect, namely nothing. This is also in vacuum, I should say, so there are no air effects or very little air effects, but this doesn't break up. Yeah? So it's not so, for liquids, this always happens. For grains, it sometimes happens, yeah? And now why is that? It turns out there are two ingredients for this phenomena. One is cohesion. So these are quite small grains, and even though they're dry, you have humidity in the air where the water condenses on the grain, so you get small capillary bridges. So they're a little bit sticky. Also, you have what's called van der Waals forces. But these forces are very small. We're talking about nanonewton forces. Yeah? That's 10 to the minus 9 Newton. 1 Newton is the weight of a chocolate, yeah? 100 grams. So we're talking about forces that are 1 billion times smaller than a chocolate bar. If you change the cohesion by, for example, covering these beads with nanoparticles that act as spacers and keep these beads apart, yeah, then you actually, this phenomenon goes away. So you need a bit of stickiness in order to see this, and you can also measure this, the stickiness with an AFM microscope, but I don't want to go into detail here, but you can measure this, but these forces are really small. Yeah? But they give rise to this macroscopic phenomenon. And another ingredient is inelastic collisions. So these collisions should also be a bit inelastic, so for it to occur, and then you can make a phase diagram where you can change both of these parameters, the inelastic collision, so that's the restitution coefficient and the cohesion force. And if you have a bit of cohesion and a bit of inelastic collisions, you see these droplets forming. If they're very elastic, these collisions, and no cohesion, you just see a granular stream. Yeah? So this is a result from some simulations. So you have now a phenomenon that looks very much like what you see in water or other liquids, but the physics behind this is actually quite different. Yeah? I mean, you can define an effective surface tension, and that turns out to be also very much smaller than you would than compared to ordinary liquids. It's also actually interesting for astrophysicists because, for example, planet formation. Yeah, you may know planets. You know, initially there's some interstellar dust, then there's gravitational attraction, and then these dust particles somehow clump together. And then these clumps clump together into bigger clumps, and eventually you get a planet. But the initial stage, how the dust turns into little clumps, is not very well understood because, I mean, these grains come together through gravitational attractions. It's very, very weak for these grains. But then, you know, they collide and maybe they come apart again. Yeah? And this, what I just shown you, is also applicable to these initial stages of planet formation, yeah? How these clumps form. Now I come to the second topic, and that is the Brazil nut effect that you probably may be familiar with. When you open a new box of cereals, right, what you often see is that the big nuts, like the Brazil nut, for example, or other nuts, they're usually at the top, and the smaller grains are at the bottom. And this is a very generic problem. It's also a problem in industry. So coming back to the aspirin tablet, if you want to mix powders, yeah, and they have different sizes, the grains, you cannot just pour them together and sort of shake it. They won't mix. Yeah, it's not like as easy to mix, like, for example, water and alcohol, which mix very well. So you have to go through some length to actually mix these powders. And because if you just shake them, they separate. Yeah, the bigger grains go to the top and the smaller to the bottom. And if you want to make tablets with a well-defined ratio of powders, yeah, ingredients, then that's not good. Yeah? So what happens? So this is magnetic resonance imaging. So you have some poppy seeds and Rajagara seeds. The poppy seeds are bright. The Rajagara seeds, they have no oil in them, so they appear dark in MRI. And what I show you here is a movie of snapshots. So I shake the container, I take a snapshot, a profile of this cylindric vessel, I shake it again, I take a snapshot, and so on. And then I string it together into a movie. And this is how it looks like. And what you get is so-called granular convection. So you have an upstream in the middle and a downstream at the side, but the downstream is very narrow. Yeah? So what happens is actually that this big particle is carried up by the upstream, but then it's too big to be drawn down by the downstream at the sides. So it's trapped at the top, yeah? And that's one mechanism for this so-called size separation, yeah? Or granular segregation. Now next, this is now the particle. This is the same movie, but now with the particle in there, yeah? And you can see how it's carried up by this upstream. Yeah? And this is one of the reasons why you see this in your cereal. Yeah? It turns out it's not so easy. This is not the whole story. Yeah? Often in physics, it's a bit more complicated the more you dig deeper. If you change, for example, the density of this particle, and you measure how long it takes for it to go up, you'll see this non-monotonic behavior. So light and very heavy particles go up very fast, which you wouldn't expect, especially the heavy ones. You wouldn't expect to go up really fast, but they do. And the sort of intermediate densities, they go up very slow. And I don't have time here for details, but the reason why this happens is actually air. Yeah? And to illustrate this, how air is important, these are two balls. One is a steel ball, one is a plastic ball. They're 1 inch, 2.5 centimeters. And so if you just tap them, yeah, you see that they both go up the same height. I mean, there's air drag, but the air drag doesn't really matter for these large particles. Yeah? Now you embed them in a granular bed, yeah, the same spheres, and you tap it again. And this, I think, is the steel one, and this is the plastic one on the left. And what you see now is that the steel ball goes up as you would expect, but the plastic ball is actually sucked down, yeah, into the bed, which doesn't happen here on the left. And the reason is that this granular medium is like a porous material, and when you shake it, the air above the bed wants to go down to the bottom. Yeah? But if these grains are small, then the air has a hard time reaching the bottom, so you get a low pressure region at the bottom. Then you have a pressure gradient, and when you have a pressure gradient, it forces this plastic ball basically downwards, yeah? Because of that pressure gradient. And this is the reason essentially for what I've just shown you, that this depends on density. I mean, there are other, I just talked here about grains, but there's a wide range of other materials that so-called complex fluids, for example, emulsions, colloidal suspensions, which are suspensions of micron-sized particles or nanoparticles. Blood, for example, is a complex fluid because it's not just an ordinary liquid, there are cells suspended in it. Yeah? And what all these liquids have in common is first of all, they can behave solid and liquid-like depending on the situation and on the composition of, but also the viscosity is not a constant. For example, water has a constant viscosity. It changes with temperature, but it doesn't change with how fast you move it around. Yeah? For this, it's different. Yeah? For these materials, it's different. Usually, the viscosity actually decreases with the deformation rate, and well, there are other phenomena. I mean, and the dynamics are quite complex. I mean, to give you an example here, this is sheared foam. These are air bubbles, yeah, and we shear them, yeah, and these on the right are trajectories of these bubbles. And you can see there are these collective correlated rearrangements, and they determine, you know, how this material flows. And if you want to understand how foam flows, you have to disentangle this dynamics and understand it. Yeah? And yeah, this is sort of active research, if you will. Yeah? So this brings me to the end of my talk. I just want to say a few words about physics at Trinity College. So the School of Physics is basically has 4 different physics courses or physics degrees. One is sort of the normal physics degree. Then there's physics and astrophysics, and both can be basically entered through the science course. Yeah? So the first 2 years are essentially the same for both of these physics courses. And then for the astrophysics people, for example, the 3rd and 4th year would be different and more focused on the astrophysics. You also have the nanoscience, physics, and chemistry of advanced materials. So this course is focused, well, as the name implies, more on the nanoscience material aspect of physics. So there's also chemistry, which there's little of here in this physics course. So you have chemistry modules and also some courses on advanced materials. And then finally, we have the theoretical physics degree, well, which focuses more on the theoretical aspects, foundational matters in physics. And this course is offered together with the School of Math. Yeah? So you have courses both in physics and in the School of Maths. And if you want to know more about this, then there's the physics stand on the ground floor, and also there's information on our website, tcd.ie/physics. Thank you.